sorry. She's from University of Haifa, and she takes what I know as adversarial learning and take a positive view on that. It's really nice work. Thank you.
Okay. Hi. Welcome to Lost Talk, survivors. Okay, so I hope it will not be very technical and you will enjoy it. It's quite fun working on it. Okay, so we all heard that deep learning made great change in everything, especially in visual recognition and other visual tasks. For example, object classification, face recognition, object localization, question answering, image description, and many others. And we couldn't do it without deep learning. And another question that we asked today, and we had quite a good answer to that, could we trust deep learning and actually other machine learning classifiers as well? And the answer was not with everything. And these adversarial examples is a puzzling thing that deep learning is still not there yet. It's still vulnerable to adversarial examples. Okay, so there are different types of adversarial examples. The one which is most popular is the one where we take a very, very small noise, which is imperceptible to human eye, and it's especially crafted noise, and we add it to an image, which is correctly classified by CNN, for example, and then we get an absolutely different label, and we can target the label or not. There are different algorithms, but if you compare these two images before adding adversarial noise and after that, we don't see any difference. And you can see these examples adding different kind of noise components, take different categories to be an ostrich. Another type of adversarial examples that also we've seen today in the first talk is the one which actually focuses on a few pixels in few areas of the image, but the magnitude is higher. And these different kinds of adversarial examples are controlled by different types of norms. The other type of adversarial example that actually to us, we see it as a noise, or hear it as a noise, but the machine learning system thinks it a legitimate category. So here, all these kind of noise images are interpreted as objects, and similar can be done with speech recognition. Same can be done with geometric patterns. So to summarize, we've already seen that adversarial examples pose security threat. A few of the applications have been mentioned today, others were not. For example, in face recognition, there was a nice paper where they created glasses, physical glasses, and put some kind of noise on it. And when you put these glasses on, the camera cannot see you. It seems that there is no face in the image, or it can impersonate to a different person. In speech recognition, a noise that we hear as a static noise is actually giving a command to the phone to do different things. Malware detection can be fooled by adversarial example, text classification. There are many other applications, we will go through it. So it's a security threat. Here today, I want to talk about adversarial examples in a constructive way, and I will talk about application to CAPTCHA, but you can also look at the last NIPS paper that talks about steganography, use adversarial examples in steganography. So to those of you who've never seen what CAPTCHA is, I'll define it. So CAPTCHA is completely automated public Turing test to tell computers and humans apart. And it could be defined as automatically constructed problems that are very difficult to solve for AI, but it's easy for humans. And there are a few examples, usually some kind of distorted text or distorted image or kind of a game that we can do quite easily, or sometimes not quite easily, but can do. And the computer and algorithms cannot do that. Okay, but here comes deep learning, and it shows that most of the CAPTCHAs, it can actually solve quite easily. So should we say goodbye to CAPTCHA? It's obsolete, we cannot use it anymore. So if we're going back to the definition, I said that it's something that is difficult, very difficult for AI, but it's easy to humans. So we propose to use adversarial examples as challenges in CAPTCHA. Why? Because it's very easy to humans, it's some of them are imperceptible to humans. The noise, we can clearly see the dog in this image. But for deep learning and many others classifiers, it would be very difficult or even impossible to say that it's a dog. It will say that it's a different category, for example, bicycle, tumbler. Okay, but from the idea of using adversarial examples for CAPTCHA to actually implement in a system or even a proof of concept, there is a long way. So we started by defining some requirements for adversarial examples, adversarial noise to be used in CAPTCHA, and these are the requirements. So first of all, it should be adversarial. What do we mean by that? It should change the category, but it should do it in a targeted way. So we'll be able to specify the target of the adversarial example, the category that will fool the system, with a specified confidence level. So we want it to be high. The second one is robustness. So we want this adversarial effect to be robust, so it will not be easy, or so it will be hard, computationally hard, to remove adversarial noise from the image or to recognize it with any other tool. What is the correct label? The other one is abandoned. The adversarial examples should be easily created, so we'll not run out of them. So we will create new adversarial example every time, and it will be easy. Perceptual small is for usability, because we want human to recognize what is in the image, and we don't want this noise to interfere with understanding. And finally, it should be efficient, because we need to create many challenges, many services, and it should be very fast to create. Okay. So we tried at that time, we tested different algorithms for creating adversarial examples, and we actually found that none of them satisfied all these requirements at once. So we needed to think, what can we do? So let's start with very simple method called fast gradient sign method that actually computes the gradient with respect to the image when the parameters are fixed. So we take a network, we fix the parameters, we compute the gradient with respect to the image, we take a sign of it, we make the noise small by multiplying by set epsilon, and that's it. We just add it to the image. So it's a very simple procedure. That's why the generation is extremely fast, and the noise is very small. It can be controlled by delta. The problem is that this FGSM algorithm doesn't define the target category and doesn't define the confidence level. It just goes away from the correct label, but it could go anywhere. So we tried quite a few experiments, and on 1,000 categories, this is a data set that is freely available, and it showed that with this algorithm, the label that we get in many cases is semantically similar to the one that we started with. So if the true label was handheld computer, and then we get to the cell phone. And for the CAPTCHA, there is a problem in both security and usability. Usability because a human can just confuse these two. And security is that we can just apply a regular deep learning algorithm, CNN, on the adversarial image, and it will tell us what area it should be, and then we can just remove all semantically different categories from the search, and then we have less guessing to do. Okay, so we established that the adversarial noise should be targeted. It should have should allow us to define the confidence level, and there are targeted adversarial noise algorithms. But they are not very efficient, and we said that they should be efficient. So what we can do is a very simple thing for this application. If we make the epsilon, the noise, larger, then we can do less steps. So maybe after that we will see this noise in the image, but it will still be small, so we can still recognize, for example, here you have the original image of the rooster and the one with adversarial noise that we did with less steps but with larger amount of noise, and in each one of them, still a rooster. you can see noise, but it's not very critical. So CAPTCHA, we tell to everyone that the challenge is adversarial examples, not a secret. So we don't really need to hide the noise, but this noise is still small enough that we can see and recognize the objects in the image. Another problem with this algorithm and many others that we tried is the following. The adversarial noise can be removed quite easily from the image. So we tried two different data sets. MNIST is on the top. These are just white digits handwritten on black background. And the other one is natural images from ImageNet. So with the MNIST, we can apply, so first of all, think about the adversarial example. I said that we add some small component. What is the small component that we add to white color? Remove from white color. It becomes gray. What is the small component that we add to the black color? It becomes gray, but a little bit lower gray. So we can just apply threshold and remove all this. And it works really well. So in almost like 95 to 97%, depending on the algorithm, you could just threshold it. And you apply the original classifier, and you get the true label almost perfect. With natural images, so why it happens? Because the entropy of the black and white images, this gray level images, is very low. If we go to natural images, the entropy is higher and the threshold doesn't work, but simple median filter with 5 by 5 size also does quite a good job. So if we apply to natural images, we can actually recognize the true label from 35 to 60%, depending on the algorithm that is used to create adversarial example. So it's not enough to be a defending algorithm, because like 35–60% is not good enough. But for CAPTCHA, if we can remove adversarial noise in 60%, so the security of CAPTCHA will be really bad. So this should be taken care of. We cannot use these algorithms. Okay, so we thought about it a bit, and we came up with an algorithm that we call immutable adversarial noise, short for IAN. And it does the following things. So first of all, it's targeted. It guarantees that adversarial example is classified with the categories that we want and with the desired confidence. And it's fast because we add larger noises at each step. And it's robust to filtering. I will talk in a moment how we do it. It's very simple. So let's just look at the example of one of these outputs that we get. We have an input, and it's classified as a sheepdog. It's not me, the network. Then our adversarial examples, you can see the noise is present in the image. You can see it, but you can still easily recognize that it's a sheepdog. And after adding this adversarial example, we randomly chosen tandem as a label, and it reached that label with high confidence. Then we filter it with, let's say, median filter. We don't care how the image looks like. We just want it to be robust against this. And the classification changed to something else, to chain link fence, but it's still semantically very far from the sheepdog. Okay, so few notations. Net of W, it's a CNN that we use to craft adversarial examples. I is the source image, C is the true class of the image, CD is a destination or a target class, and P is the confidence level of the new label of the C. So we put all this as the input to our algorithm, and it outputs adversarial examples. The algorithm is actually adds iteratively noises with some epsilon and then clips them. So this algorithm is very similar to what was proposed by Korakin et al. In 2016, but we did it at the same time, more or less. So, okay, it's very intuitive. So what we add to make it robust to filtering, we filter it, and then we try to recognize it with the network. If the network gets the true label, we increase the noise and go to the iterative stage again with the increased noise. And we continue doing that until the filtered image is no longer recognized with a true category. And then we're done. We have
And you add the noise, the additional noise you add to the filtered one?
no,
or
to the original one. So when we can filter the image, then we just increase the noise by some epsilon, and we go again. So that's a trade-off between usability and security. So, okay. Okay, so this is about the pre-processing attacks, that you can just actually run filtering, and we did this adversarial, this EN thing to prevent filtering attacks. What about other machine learning methods that can be applied? So what we call defenses in the community of adversarial examples, or defenses against adversarial examples. So you heard today during the first and second talk that adversarial examples are tricky. It's really difficult to find defenses against them. So because they generalize very, very well between different deep learning architectures. You can craft them with one architecture and they adversarial for others. Different training sets. You can craft them on one training set of the same classification problem, and then you can apply it to a different one. It works quite well. Adversarial examples can be constructed for most popular classifiers. You also saw it today: logistic regression, linear SVM, but also for decision trees and KNN. And adversarial examples that are trained for constructed for one classifier can fool other classifiers, which allows black box attacks. But for our means, it's good because if we do adversarial example for deep learning, other tools will be unlikely to classify. Then we will see in a moment. What can be done which is more effective? One thing is, it was noticed that RBF models, they're very non-linear, are more robust empirically to adversarial examples. But if we set up our problem with large enough classification problem, then these models do not scale up well. Meaning that these RBF models cannot easily solve 1,000 category recognition problem. And humans can do it quite easily. I'll show you the usability test. We can recognize 1,000 categories very well. Adversarial training was also shown to be somewhat helpful against adversarial examples. However, if we do a new generation of adversarial examples after we already trained, so the network was trained on adversarial examples, now I craft new adversarial examples to the new network, then it fools it again. There, in last year, or maybe last 2 years, there was some research on trying to detect adversarial examples. So it's kind of a binary problem. It's an adversarial example or not. There was quite a success. However, it's irrelevant to us because, again, it's not a secret that my challenge is an adversarial example. The problem is to recognize the true label, and this method do not do that. They could just say, okay, it behaves differently, so it's an adversarial example, but, well, you already know that. Okay. And the last thing that we ask, so it's not in the same order, is that the adversarial examples should be abandoned, and we know from previous research that they occur in broad spaces. And I want to show an example, illustrative example with ENs. So I took an image of snow leopard, which was recognized correctly by CNN, and I took two directions in a gradient space. One on the top and one on the bottom, and the x-axis shows the amount of noise I add. So you can see that if I add a little noise with low magnitude, you can't see the noise, but if you go on the other side of the slide, then you can see the noise quite large. But you still can recognize the level. So let's see what's going on here. So on the top, the whole direction is incorrectly recognized as orange. And on the bottom, that even changes the classification label when I add more noise. So for small noises, it says it's hair slide, and for larger noises, it says it's a hermit club. And this is, you can go to many directions, and it changes with the direction, and it changes with the amount of noise that we add. So these are, we can actually get many, many adversarial examples even with from one image. Okay, so now this is algorithms that we use in our system. We call it DeepCAPTCHA, and this is for generating the challenge. So we assume n classes. So in our case, we use the 1,000 classes, and we pick randomly one of these classes as the source image. So let's say I is one of these classes, and we acquire the source image from some kind of source, from the web, some crawling service, something like that. Okay, then we randomly pick a destination category, the targeted category. It should be obviously different from the original one. And then we generate adversarial examples that I showed you before. After that, we throw away the original image. We don't use it anymore. We don't store it anywhere. And then we select the answers that we show to the users. We don't show all 1,000 answers. It's just too much. I'll say in a moment what is this M means. But we show M answers. Out of these M answers, one is the true category, and the other ones are just randomly selected from the original N categories. We don't include the destination category because an adversary can just run a CNN on adversarial examples, get the category, and then will remove one of the answers. So it will remove the chances for random guesses. Excuse me, increase the chances for random guesses. So we actually remove I, remove D, and from this set we choose M-1 categories. And we present them as pictorial answers, and I'll show you in a moment. And the task of the user is just to click on the true answer. And few implementation details. As I said, we use some subset of 1,000 categories from ImageNet, and we used VGG network for object classification and to create the adversarial examples. And we trained the network on the training set of this set, and we crafted adversarial examples on the validation set. So again, this one is just for proof of concept. If you want to do a real system, you cannot store your source images. You just need to take them randomly from some web service and then throw it away. Okay. So this is a snapshot from the system. And we show the adversarial example, the challenge on the top, and then we have 12 answers that we present to users. As I said, 11 of them are chosen at random, and one of them is a true one. And you can see the one with the red box, this is a true answer. So it's not exactly the same image, it's a different image from the same category. So it wouldn't be a problem for deep learning to recognize it, but because of the adversarial noise, it's impossible for the deep learning to. And this is another example, and you can guess where the true answer is. It's in the white box. And one more example, the chest. It's only one here. Okay, so we ran a usability study using a crowdsourcing service. We asked quite a lot of people. I don't remember the number exactly. And we tried this with different number of challenges, with different number of answers. We varied from 8 answers to 20 answers, and we asked them if this proposal is simpler, easier than previous CAPTCHA, similar or harder. And it depends on the number of answers, but if we use 8 or 12 answers, then the users said that it's or similar or even easier than previous CAPTCHAs. And self-reported usability, 10 was very good, and 1 was very bad, and people were happy with the usability, as you can see. Okay, so security analysis, we tried different kinds of attacks. We first analyzed a random guessing attack, where we set the number of challenges and the number of answers, and we see what is the false acceptance rate. I'll show it in a moment. We tried different image processing techniques to avoid removing the adversarial noise, and we tried various machine learning attacks. So in random guessing, the probability of guessing m answers in n challenges. So if we present not one screen and several of them, n of them, is 1 over m in the power of n. And then we set this probability to 1.5% as an acceptable one in CAPTCHA. And if we use m equal 12 as the number of answers, which was had good usability results, we get that the number of challenges that we show should be higher than 1.69. So we set n to be 2, and then go with this analysis backwards. We get the false acceptance rate. The probability of false acceptance rate is 0.7%. It's not the probability, it's percent. So it's very small. So if we set 2 challenges with 12 answers, random guessing is not going to help us much. Okay, then we tried filtering attacks. We tried different filters. Some of them are very simple, just took from MATLAB. Some of them are more complex. And as you can see, the success rate, we tried on 1,000 different adversarial examples, and it goes from 0 to 0.3%. It's very low compared to 60% that we had in previous methods. Okay, so before I talk about machine learning attacks, I will introduce the attacker model that we assume here. So we assume that the adversary knows the CNN, the white box. It knows our algorithm for creating adversarial noise. It has access to all DeepCAPTCHA challenges, but he doesn't have an access to source images, so they're not coupled. And also we assume that he can use any machine learning or whatever tool to attack the DeepCAPTCHA. So if we want to use an alternative classifier, it should be more robust to adversarial examples in general, or at least to those that we use in DeepCAPTCHA. And it should be scalable to a large number of categories, because our recognition task is 1,000 categories. So if the classifier is not good enough to recognize 1,000 categories, it's not going to help the adversary. So as I said, RBF models, they satisfy the first one. They are more robust to adversarial examples than others, but it cannot deal with 1,000 categories. Due to transferability of adversarial examples to other architectures and other classifiers, they have low chances of success in attacking the CAPTCHA. So we tried this is in general, we tried it on 3 different deep learning architectures. So we used BGG for crafting adversarial example. There are 3 different architectures, and the adversarial success on our images created with EN was from 0 to 0.1%, so it's very low. We also tried other classifiers. So it's a large problem, and so we tried something simple just to show that it's impossible. We tested it on bag of visual words with linear SVM, and you can see that the adversarial images, the success is a little bit better, but it's still negligible, 0.5%. Another thing that could be applied to be robust to adversarial examples, as I said, is trying adversarial training. But to perform adversarial training, the adversary needs the true labels. So if he downloads the images from our DeepCAPTCHA, he still needs the true label for that. And to do that, well, the adversary needs to hire people. And then it's higher cost. The whole idea of embedded captures is actually to remove the cost. So we can do also adversarial training, and because we do know the labels, and we can update our network every once in a while with adversarial examples. So we will be ahead of the adversary who will try to do it anyway. We tried this attack, some variant of this. So we tried the iterative process with 2 steps. In the first step, we produce adversarial examples using the current network. And and then we add it to the pool of adversarial examples. Then we retrain or fine-tune the network with a mix of clean and adversarial examples. We ran it for a few iterations, for 5, adding 2,000 adversarial examples in each iteration. So when we check the robustness of adversarial, of this adversarial training on previous generation of adversarial examples, it went down from 100%. First, before that, they fooled it in 100%. Now they fooled it in 92.3%. But we took this architecture, they're not actually trained with adversarial examples, and we created a new generation of adversarial examples, as I said, and they fooled the network in 100%. So it's not really a good attack. What can be done to actually a little bit improve the robustness is to use ensemble of all these 5 networks, and it goes down from 100% to 98.9, but still under 2% acceptance rate is not a big problem for CAPTCHA. Besides, we did very simple thing here. We can also improve it, the robustness of against ensemble using recent methods for training adversarial examples for ensemble of models. Okay, and the last one is actually quite a curious example. I call it noise approximation. So what I do here, so as I said, we create a noise for changing the label of the adversarial example to something else. So here we have an image of 1, which was correctly recognized by CNN as 1. I added an adversarial noise, and now it recognized as 2. Now, what I did, I took a different image, different adversarial examples that would recognize as 2. Do I have a point? No. Yes? This one? Yeah, this one. Okay, it's recognizing 2. And I subtract the same adversarial noise I created for the first one. So this is the same adversarial noise. Now I get an image that is recognized as 1. So I actually cleaned an image from adversarial effect by subtracting a noise created for a different image. So you see that these 2 images, this one and the one on the top, are different images, but it worked. And it's not a universal noise. There are some kind of universal noise adversarial and universal noise that you can train against many different images, many different classifiers at once. This was created just for the first example, and it worked for the second. So how can I turn it to an attack? I can create sets of adversarial noises that transfer one category to a different one. So for example, here I will create a set of adversarial noises that transfer image recognized as 1, the true ones, to adversarial 2s. And then I will do it for each class. So I will have a set of noises transferred 1 to 2, 1 to 3, 1 to 4. It seems like a lot of work, right? I need a number of classes times number of training examples that I used for these noises. And then in test time, I'll just try all of them until I get a success. So it's lots of work, but it turned out, or we tried 200 training images and 200 test images transferring 1 to 2. So again, I create 200 noises transferring different images as 1 to, so that will be recognized as 2, and I try to remove from 200 different images these noises. So it worked in 100%, and in 90% it worked on the first attempt. So actually I can randomly pick some kind of noise created for one image and apply it to a different image and remove this adversarial noise. So from this, I conclude that MNIST is a horrible data set to use for checking the protection, to actually benchmarking the protection, benchmarking adversarial examples. And the troubling thing is that all papers that you will see in this topic. MNIST is the first thing they tried. And there are quite many papers that try only on MNIST. So you can see threshold removes. You try with adversarial, different adversarial noise removes. You just look at it long enough and it removes. Everything works. So we should be very careful and not use images which have very low entropy for this kind of attacks and defense. So I tried the same attack on real image, on natural images, trying to transfer lion to rooster. And here's lion. I create an adversarial example, which make it recognized as a rooster. Then I take another lion that was transformed to a rooster with the adversarial noise. I tried to subtract the first noise, and it remained rooster. It didn't work. So I did this attack on a larger scale, and as you can see, it has very low success of 0.25%. So this attack doesn't work on natural images. Okay, so even though numbers and characters were used in original and in classical captures, for this kind of application, these images are not good enough. They don't have enough entropy, so we should not use MNIST or any other similar data set for that. We did use something that we could find, and it was this ILS-VRC data set, which is a subset of ImageNet that has natural images. It has enough entropy, but it has another problem. They have quite many categories which are very similar or culturally influenced. And this is a usability problem because they have like all these kind of dogs or different kinds of animals that look to me exactly the same. So it's one of the examples. So you have a bird there, and there's another bird in the answer, which one of them is correct one, the other one is not. So it's a problem in usability. It also could be a problem in security, because if you look at the top 5 classification, even though the top 1 was changed, it's still similar categories could appear there. So a good thing for someone who wants to implement it is to actually collect a new data set with many categories, but which are not similar to each other. So you can go to this web page and you can try it. It's online and it's quite fun. My children liked it a lot. Another thing that I didn't show here, our usability analysis showed that women actually much better in this than men. They do it faster and they do it better. So, well, it's another interesting fact about adversarial example. Thank you.
Did you consider that the attacker can learn from the feedback of your system and then bypass the perturbation of your system? For example, you said that the attacker doesn't have access to your images, but actually he does, because he sees your images in real time, and he can, by that, maybe assess your perturbation algorithm.
My perturbation algorithm is not a secret.
It's not a secret.
No. But from a perturbation algorithm, you cannot get back to the original label.
But in a way, like the attacker can understand, can the attacker use the images that the system shows them and query it many times and then have all the images in a way, and do something with that, or not?
You can do many things with them, but you don't have the true label.
Okay, and another question. You said you didn't want to use the destination label because of random guessing, but did you consider that maybe you can identify an attacker just by having the destination label, and then you can use it for detection in a way?
Yeah, it's a good idea.